We talked about that there were different ways of transforming images one to another. And, so I might have two images that are related by some transformation. And we talked about how if I know the transformation, I know it'll go from one image to the next. But suppose I have two images, and I'd like to figure out the transformation that takes image 1 to image 2. How would I go about doing that? Well, to do this, I need matching or corresponding points. So the way we're going to go about finding corresponding points is using something that we're going to call local features. And you'll notice it says a little 1 and a little 2 there. We're going to put some meat behind defining what we mean to be like local and what we mean to be features. By the way, some of you have taken machine learning courses and things like that, and you've seen feature vectors. That's not what we mean here. We're actually going to mean that later in the course. Here, features are going to be things that we compute about some little local spot. They're related to feature vectors, but we were here first. All right. Our goal is to find points in an image that can be found in other images. And by the way, not just found in other images, but found precisely. And what that means is, you tell me about it. I should be able to precisely determine where that point is. So just saying it's the middle of this gray panel, not so great. But if you told me it's this tip of this spear, that would be better in terms of being localized. Also, I want to reliably do the matching, right? So if I find this point, if I find a bunch of other points, I want to be really sure they say, nope, it's not this one, it's not this one, it's definitely that one, right? So this is this idea of well-matched points, all right? So why do I want to do this? Well, we talked about things like I might want to recover the fundamental matrix to recover geometry. Remember we said that if you give enough correspondences. In robotics and other computer vision things, we might want to see how a bunch of points have moved from one frame to the next. And in order to do that, I have to figure out which points were which. Or I might want to build a panorama. Now, we've talked about this in general, but here's really a beautiful example. This comes from a paper by Brown and Lowe in ICCV in 2003. Let me just play that again because it's so cool. All right? And here what they've done is they've figured out with matching points how to place each one of the pictures on top of another. In order to do that, they had to find these matching points. Let's step through this just a little bit. So when we talk about building a panorama, what do we have to do? Well, we're going to have to sort of align our pictures in order to be able to paste them together. That's what we just saw. So to do that, here's the basic process. The first thing we do is we're going to detect some features, okay? And here features just mean some interesting points. In fact, we're going to define something called an interest point operator that'll find some points that we define to be interesting. Don't you wish you had an interesting person operator? You could just scan it around a room and it would just tell you who's interesting. It wouldn't go off a lot in my house. Anyway. No, sorry, hon. So here we've detected a bunch of points in both images, and these are going to be our feature points. The next thing we have to do, and just looking at this, it looks a little bit like a mess. We need to find the corresponding pairs. That tells us how we need to transform one image to the next. And then we can use those pairs to align the images. And if we do them in this particular example, you get something that looks like this. By the way, the seam has been left in here just to make it clear how that image is being moved. If you were actually splicing these images together, you would do something, sexy in order to make sure that those seams became invisible. Now, to do this detection and matching and alignment, there are a couple of things that we have to worry about. The first problem is, well, I can't possibly match points if I don't find them in both images. And remember, I'm going to detect interest points here and interesting points there and look for a match. So it better be the case that a point that's been found here to be interesting is also found over there. In this particular case, there would be no chance to match because I found some set of 4 points on the left and a different set of 4 points on the right. So what we need is what's referred to as a repeatable detector. If I run on this image, most of the points that I find over here as being interesting, I will also find over there, and vice versa. So that's the first problem, reliably finding them at all. The second problem is, let's assume that these points on the left are somewhere in the right. So I found here it's 4 points on the left, and then there's 4 points on the right. Which point is which? Okay, I have to do the match. The way we do that is what's referred to as using a descriptor. A descriptor is just what it sounds like. It's a description of a point, or of a feature to be precise. What I want are distinctive descriptors. That is, if I write down the description of each of these, so you can think of the description as being the name, right? So I want this one to be Bob, Ted, Alice, and George. That's mixing some metaphors from the 60s, by the way. Because if they all said George, 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 and this one says George, then I've got a French movie, and I don't know what's going anywhere, okay? But if this one says Edward, it better be that one of these things says Edward. Maybe if it just says Ed, I'll be okay. But my descriptor can't change that much of the same point in the two images. So that's what we talk about it being distinctive, Bob, Carol, Ted, and Alice. That's who it was from the movie, right? They have different names, but they also have to be reliable. So Ed might become Edward, but Ed doesn't become Francesca. All right. So feature points are used for all sorts of operations in computer vision. Image alignment, we talked a lot about. 3D reconstruction. Motion tracking, I'm trying to figure out how either the object's moving or the camera. Object recognition, in fact, in a couple lectures from now, we're going to take some features from a bunch of different objects, take the features in our image, and figure out, it's this object that's in that image. All right. Database, indexing, robot. Features are used for all sorts of things, and that's one of the reasons why we have to talk about them in the class.
Here is a section of the Berlin Wall, photographed from two different angles. I've marked some candidate regions in both images. Select the ones that you think can serve as good features. Note that when evaluating the fitness of an image region, you're only considering the pixels within it. Let me get you started. This gray patch at the bottom left is pretty bad. This nose in the right image is fairly distinguishable. So, any region with two or more edges coming in at different angles is a pretty good feature. Like this fat lip that shows up in both images, corner behind the ear, base of this nose in the left image, green corner on the pink wall, also in both images, and this top section of the wall in this right image. The cropped portion of the eye is also pretty good. So is this tooth that shows up in both images, although it could be hard to match given other teeth that look similar. These two regions involving the cycle and cyclist in the right image are useful as well. However, they're missing from the left image. Now look at the remaining regions. This one with the vertical edge in the left image cannot be located precisely. Same for these two regions with horizontal features. Also, this diagonal could be anywhere along the wall. And even these two with slight curvatures are no good. They could be part of larger curves and would be hard to localize. So, what makes certain image regions good for feature matching and not others? Think about any common properties you can see. How would you define these mathematically?
What makes a good feature? So here I have a picture just as an example. The first thing is, it's called repeatability/precision. The same feature should be found in several or multiple images of the same scene. Now, of course, these aren't all the same picture, because if I gave you 15 copies of the same picture, this would be a really boring class. All right? These are actually different pictures of the same scene, so things change a little bit. But despite those changes, I want to get the same points being identified, and that's repeatability. And also, I'd like it to be the same point, right? So there's this little red dot on top of the camera. There's one over here, too. I wonder which one I'm looking at. See, I'm going to make Megan cut back and forth in her video. Okay, the little red dot. So that dot's a pretty good feature because there's only two of them that I'm looking at here, so I can find both of them, and the matching will probably be easy to do. And then they're very precise. That is, I'm not going to drift around. I'm going to be able to find right on that dot. The next thing is salience or matchability. This is how distinctive the descriptor is. So each feature should be able to be described uniquely enough that it's easy to find it, right? So if I'm looking at a bunch of white dots on a black wall and they're all the same white dot, that's really a problem, because that's the George problem, all right? Everybody's named George. I can't find anybody. I just quit and go home. All right? So you'd like to have a description that's different about them. Compactness and efficiency. Another way of saying this is don't get carried away. You remember when we talked about computing the fundamental matrix, we said, well, I only need 8 corresponding points, but I mean, maybe having a dozen or 20 of them might be better. Maybe even 50. But 50 is much smaller than the number of pixels in the image. So what I would really like to do is, in general, I don't want to have a feature everywhere, although in this picture there's a lot of them. But you see, even here, it looks like there's a lot of them, but I don't know, maybe there's 100. But there's tens of thousands of pixels here. So that's what it means by being compact and efficient. And finally, locality. Locality is not what you think if you think locality means exactly knowing where it is. That was the precision. Locality means that the descriptor that I compute about the feature, the description, the name, is based upon information that comes just from a pretty small area around the feature. Now you might think that, I'd like to take a nice big area to describe it, because that'll give me a nice, very distinct description. That's like a first name and a second name and a third name and a fourth name. It would give me a very rich description. The problem is, and I'll try to find, oh yes, right over here. So I'm looking at the side of this. Now I hope I'm still in the feed. No, that camera moved. I'm looking. Okay, good. Thank you. So I'm looking at the side of the lens over here, and the problem is if I take too much of the lens to describe what's going on, as I move over here and I start to get occluded, a bunch of that neighborhood goes away. That's the same thing as when we had, a finger getting occluded a little bit by the other. So since I'm trying to find matching pixels from different views, and different views will cause a little bit of occlusion to change, I don't want the neighborhood that I used to describe to make the descriptor to be too large. And that's what locality means. It makes us more robust to sort of clutter and occlusion. So, believe it or not, that's the end of this first lesson. Why? Well, I want to cut your break a little bit. Actually, the real reason is the next lesson's got, shall we say, a modicum of equations on that, and to do this and then all of that, boy, that would be too much, so here we are. But the idea is that we've motivated what it means to be a feature, and a good feature. Features are being used to match one to the next. The two main properties that we talked about is repeated detectability. That is, if I find them over here, I'd like to make sure that I'm going to find them over in this image. And they also should be good for recognition one to another. That is, you can think of them as having a signature, and that signature should be distinct, right? Bob, Carol, Ted, and Alice, all right? But robust, right? So Edward might become Ed, but nothing significantly different beyond that. Turns out that this notion of being both distinctive and robust sort of works against each other, and we'll talk about that. So going forward, we're going to introduce about what it means to be a good feature, what it means to be a good interest point, and we'll break that down into two parts: detecting of interest points, and then characterizing the descriptor around those interest points. So sharpen your lead pencil. You guys even seen lead pencils anymore? Don't use a lead pencil on your iPad. It's probably a bad idea. And we'll do some interest point operators and how those function mathematically. Welcome back to Computer Vision. Today we're going to talk about finding corners, which might not feel like the most exciting thing in the world, but actually it is fundamental to a whole bunch of computer vision. Last time we talked a lot about the notion of features, and features were sort of locations in the image that you could find in multiple images so that you could match them, whether you were doing essential matrix finding or some other reason or some transformation. And we talked a little bit about what makes a good feature. So here was an example of some feature points. The first thing that makes a good feature is simply repeatability / precision, but really repeatability meaning if I find you in the left image, I better find you in the right image. Or if I have a sequence of images that I'm trying to line, I want to find that same feature point. I want to detect it as a point in as many of them as possible. The other thing is that I should be able to be sort of precise in my description. We'll talk a little bit more about locality in a minute. But the idea is that, this is the point. I find it every time, and I find it more or less in the same place with respect to the scene. The next thing we said needed to be important about a feature was the saliency or the matchability. And what we mean by that is that it should have a description that's distinctive. So when I find it in one image, when I look in another image, there aren't a lot of other points that might match that first image. The description should be distinctive. Something that we sometimes forget is that one of the reasons we're doing this, finding these features, is that we're going to use this, I think I used the term constellation of features. This collection of features is going to stand in for the image. So if you remember for fundamental matrices, we needed 8 points, although a dozen or more is better, 20. But the idea is that this is a number much smaller than the number of pixels. So compactness and efficiency says we should find good features, but we should not find a bazillion of them, or even half a bazillion. We should find enough, but not too many. How's that for a technical description? But the idea is that you're finding enough, but it's much, much less than the number.